Hello everyone, and welcome to the 181 video on regularization. So again, we'll split it up into three parts. We'll start with motivation in blue, then intuition in red, and then the math in purple. So why do we need regularization? So let's start with a problem called overfitting. So imagine that we have some data below. On the y-axis is what we're trying to predict, and on the x-axis are the covariates that are fed into our model. And although we only have one x-axis, we'll use this type of diagram throughout the course to represent lots and lots of different dimensions of x data. So there might be like 5 or 10 dimensions of x data, but we're only going to draw it like this so that we can actually visualize it, since we can't visualize so well in higher spatial dimensions. So if we were just trying to do a linear fit, just like the linear regression that we discussed previously, we might have some sort of fit that looks kind of like this, and that will work out pretty well. But when we have an overfit model, let's say we have a lot, like a high dimensionality of x, and let's say that dimensionality is actually so high, then what our model can end up doing is it can end up fitting each of these points exactly. So here, instead of learning the relationship between the data, like is happening with our black line, that they generally increase together, instead we're giving the model so much power that it's just memorizing the shape of our input data. And this can be a problem because let's say we want to make a prediction about some new x value right here. Our overfit model will predict this value here, whereas a more accurate model will probably predict something around there. So our overfit model is going to not have strong what we call generalizability, or ability to predict things outside of the initial data set. We also call that like high out of sample error. So the reason we model these things is because we want to be able to predict things, but if our model overfits the data, it won't be able to predict things because it's not capturing any relationships. It's just memorizing the actual data. So it'll perform really well on our training data, but it won't perform very well outside of that. So how do we fix this? So in order to fix this, we want to penalize high weights, right? Because basically, if we're allowing our model to pick any weights it wants, then it can use those weights to memorize the data points. Whereas if we restrict it to only using smaller weights, then it has to be careful. It can't use as many of the dimensions of the data as we give it, and it can't completely overfit to the data because it's somewhat restricted in terms of what coefficients it can actually choose. So here below, I've written out a loss term, and you'll see the first term in the loss is exactly what we had. So that's just L2 loss. And then the second term here is what's important. So the second term here is an additional term that we've added to the loss. So remember, the motivation for loss was like we want the algorithm to minimize how much mistakes it's making if it were to predict our training data again. And now we're also going to say we want to penalize the algorithm if it chooses lots and lots of really high weights. So I've written out a general formula for loss here. So we have a parameter lambda, and the lambda parameter is just sort of how much we care about regularization. So the higher it is, the more regularized it will be, the smaller coefficients that our model will choose. And then we have over 2, right, similarly to what we discussed in the linear regression video, that this just cancels out mathematically. And then we take the magnitude of the weights, and we can either just take the magnitude of them, and this is called lasso regression, or we can take the sum of the square of the weights, which is called ridge regression. And those are both valid ways to do regularization, and they'll end up with different sorts of results, which we'll discuss in a little bit. There are lots of other ways to do it. There's something called elastic net, which uses both lasso and ridge. And there's also, you can also regularize just by an indicator function on how many of the weights are non-zero. So you can try different things, and you should pick the thing that's sort of best for the scenario that you're working in. So how are lasso and ridge regression different? So lasso regression is often a lot more sparse. And what do I mean by sparse? When I say sparse, I mean that a lot of the coefficients will be 0. Whereas in ridge regression, a lot of the coefficients are usually not 0. And it's nice to have sparse because one, this can tell you sort of which variables are the most important. It can help with like selecting variables. And two, it also gives your model a little bit more interpretability because you can say, you know, like these are 3 or 4 factors are sort of what's affecting the thing that I'm trying to predict or correlated with it, right? You can't necessarily make causal conclusions. But why is lasso more sparse? So if we take a look at this diagram right here, what we'll see is on the left is the lasso penalty. So like we're pretending that we only have 2 dimensions, like that W is only 2 dimensions, and this diagram here uses beta instead of W. And in light blue is shaded the region under which there is a penalty, under which the lasso or ridge regression term will be less than or equal to 1. And so what you see here is that on the left is lasso, and it's just basically a square or diamond. And the right is ridge, which is more circular because the penalty is proportional to a quadratic term. And so that means that if we look at sort of like the level sets of performance of our coefficients, they're going to more often coincide with our regularization terms. For lasso, it's going to coincide in a place where, you know, one of the coefficients is 0, whereas with ridge, it's not going to do so. So how do we do this? Let's move on to the math behind how would we solve for our W. So ridge regression is actually very similar to linear regression. I would encourage you guys to do it on your own, but I've done it below. So again, we are going to take the gradient of the loss function. We're going to set it equal to 0. So here, these first 2 terms, just like in our first video, come out to negative xty plus xdxw. And then our second term is just lambda w, right? And that's because the derivative of the regularization term will just be lambda times times 1/2. Okay, so we don't have the 1/2 for, okay, that's fine. Yeah, so that will be the regularization term. Cool, and so we're just going to rewrite this. So moving the x to y to the other side, and then writing xtx as m, just it's a little bit more convenient notation. If you see sort of where I'm going, you can just go ahead and skip to that step, but just to sort of show how I do this matrix simplification. Then we notice that here on the right side, this actually just ends up being a vector, right? And so we can write out each of the terms of the vector. So it's going to be w times the first row of m plus lambda w1 will be the first entry. Then the dot product of the second row of m and w plus this lambda times w2 all the way down. And what we see is that actually we can rewrite this. This is just the w vector times m plus lambda times the identity matrix, right? We can see that because the identity matrix in the first row has a lambda and then lots of zeros. So multiply that by w and you get lambda times w1. The second row, it'll give you lambda times w2. So that corresponds to this second column here. And so then we just move that to the other side, and we get that the analytic solution for w is the inverse of xtx plus I lambda times xty. Cool. So again, you might be wondering, how do we know this is invertible? Which is always a great question to ask. So we're going to show that that xtx plus I lambda is positive definite. And so this is pretty similar to what we did for linear regression. So fixing some vector z that's not equal to 0, we remember that we should show that z transpose times the matrix times z is greater than 0 in order to show that's positive definite. So we just distribute out the z, and then we see that each of these is just an L2 norm. Here there's a lambda term that we just move outside, and then we get that the L2 norm of xz plus lambda times the L2 norm of z. And so we know that the L2 norm of z itself must be greater than 0 because z is not equal to 0, and also lambda is a non-zero, or lambda is a positive integer, so by choice. So that means that this second term, the entire thing, is greater than 0, and the first term we know is greater than or equal to 0 because it's an L2 norm. So overall, this is greater than 0, so that means that this matrix is positive definite and therefore invertible. Great. So again, just that's for mathematical side. How do we know it's invertible? But the important result is the actual closed form analytic solution for W. So now we want to take a look at lasso regression. So lasso regression is a little bit more difficult because we just have an absolute value. So how do we solve this? There are a couple different ways to solve it. You can solve it with quadratic programming. I'm going to go over a way called least angle regression, and I'll sort of go over the general technique. The actual proof of correctness for this is like relatively involved. If you are more interested in it, I would encourage you to read the paper. So basically, the strategy is going to be like we're going to look at all the different x dimensions. We're going to pick the one that's like most correlated with the residual, right? Because that's like if we have an error term, we want to start and increase the coefficient for the x dimension that's most correlated with that until we run into issues. So first, we're going to initialize all the weights to be equal to 0, and we're also A is going to be the set of sort of like x dimensions that we're working with. So the first x dimension that we want to work with is just the one that's most correlated with y. And so until we've sort of until we've gone through all the predictors or all the x dimensions, we're going to do this sort of iterative process. So we will just so all of the A we call the active set. So for all the dimensions in the active set, we'll increase their relative coefficients, Wi. In the actual paper, this is referred to as the equal angular line, but intuitively what you can think of is we've picked the dimensions that sort of are most correlated with the residual, and we're trying to shrink the residual down. So we want to kind of increase in the dimension that's right in the middle of all, or increase in the direction that sort of splits the difference between all those dimensions. So that's why it's an equal angular line. We're increasing in the direction that's in the middle of all of those dimensions. And we're going to keep doing that until either one thing that can happen is there is some coefficient right in the active set, and it's going to go from non-zero to 0. So that means that like moving towards the residual was actually making its magnitude smaller. So when that happens, then we'll just remove that from A, and we will continue moving. But now we'll adjust the equal angular line, right, to be in the middle of all the stuff that's still in A, so everything except for I. The second thing that can happen is that there can be some other k that's not in the active set, and xk becomes as correlated with the residual as the members of A. So then we just add that to the active set and continue on the equal angular line, now considering k. And so basically this ends up having the exact same behavior as the lasso regression, which is really interesting. And so yeah, that's sort of one possible solution to lasso. Awesome.